If two or more capacitors are connected in parallel, then the total capacitance of the combination is increased. Because they're connected across the same supply, each experiences the same potential difference. Each one will gain a charge described by this standard equation. The total charge will be the addition of each of the individual charges. It follows then that the total capacitance is the addition of each of the individual values. When capacitors are connected in series, each plate will have on it an identical charge, and the total potential difference across each capacitor will add up to the potential difference across the supply. We can rearrange this general equation, C equals Q over V, to give V equals Q over C. If we then substitute Q over C for voltage in each of the terms of the equation, we can take a second step cancelling out Q, because the charge on each of the capacitors must be identical. The final equation for each of the capacitors in series looks very much like the equation for resistors in parallel. Be careful to avoid confusion. When a power supply is connected to a capacitor, it does not charge up instantly. The amount of current that flows to it is limited by the amount of resistance in the circuit. The amount of charge it can accept depends upon the size of the capacitor and the potential difference of the power supply. We have set up a series circuit with a power supply, a capacitor, a resistor and an ammeter in series. Also available is a digital clock displaying seconds. The values of the components are given on the diagram. What we have not done on the actual circuit is finally make it a full connection. And we're going to do that here. You can see the capacitor and the resistor. They're very small components physically. And we're going to make the final connection and record values of the current against time. You can replay the video so that you can get accurate values of the current at fixed intervals of time, perhaps every 5, 6, 7 seconds. If you record these values and put them in a table, simply current and time. For consistency, try and take the value of the current that is on the meter as the clock second changes. The values of the current that I recorded are shown in this table here. You need to draw a graph of time on the horizontal axis and current on the vertical axis, either from a spreadsheet or by hand. From the graph we're going to try and calculate the time constant. The time constant is defined as the time taken for the charge on the capacitor to drop to 37% of its original. That'll be the same as the current dropping from its original value to 37%. You can see that calculated on the graph, and we're going to mark that in. From that measurement, the approximate value of the time constant seems to be about 10 seconds. But we can repeat this by finding 37% of 195, and then again 37% of 72, marking these points in on the graph on every occasion. Repeating this exercise 3 times gives us a more accurate, or at least more reliable, value. We have a value of 31.5 seconds for 3 time periods. That's an average of 10.5 seconds. The value of the time constant calculated from the components is C times R, and that is equal to 10 seconds. So the two values correspond nicely. Additional explanation of this is available on the worksheets that are provided.